In this lecture, you will learn what the main difference is between traditional machine learning algorithms and representation based machine learning algorithms. We've looked at how traditional machine learning models work. Let's now contrast it with deep learning and see how they differ and see what the advantages are of deep learning models. If your objective is to build a classification model, as a first step, you'll choose the classification algorithm, one which suits your requirement. You'll feed it a whole bunch of training data, that is the corpus, and you'll end up with a machine learning based classifier. Once you have this classifier, though, in order to make predictions or even in order to train your classification algorithm, you'll need to determine what features the classification algorithm should pay attention to. So, the actual feature selection for your machine learning model in a traditional model is done by experts such as you. And really, this is the key to how traditional machine learning models work. ML based systems, which still rely on experts to decide what features to pay attention to. You can't just throw it a huge mass of data and expect it to figure out by itself what is important within this huge ream of data. Early on, when we didn't have such huge data sets available to us, this may not have been a problem. However, in the modern world, we collect data from all kinds of sources. Let's say you have car sensor data or you have weather data from thousands of stations across the world. Because we have such huge data sets available to us, it's almost impossible for us to parse through and see what is important within a data set so that we can construct our machine learning model. We need something more intelligent. We need something where the actual feature selection of what is important within our data is done using a feature selection algorithm. And really, it is this automating of feature selection using a smart feature selection is what sets apart representation ML based systems from traditional ML models. And this is where representation ML models are much smarter than the traditional algorithms that we've used so far. Representation systems figure out by themselves what features to pay attention to. You can simply throw data at a representation ML model and it'll parse out and sift through and find patterns within this data without having you point out what features are important. Here is an analogy of how a representation based system might work. This is not to be taken literally, of course. You can imagine that the ML based binary classifier built using a representation model simply needs to be exposed to lots of images or maybe even videos of whales and a variety of other mammals and fish. Based on all the characteristics that it observes within these images or maybe even videos, it should be able to determine that the whale is a mammal. You haven't pointed out what characteristics are important. It should be able to figure this out by itself. And this is where deep learning comes in. Deep learning systems are one type of representation systems. Here are some basic concepts that we'll cover in this video and some of the videos which follow this. The first is the idea of deep learning, which are basically representation algorithms which look at a huge data set and figure out what features are significant, what features matter. Neural networks are one kind, or in fact, the most common kind of deep learning algorithms. Neural networks are modeled on our neurological system and are made up of active learning units called neurons. Neurons in machine learning are built to mimic the working of neurons within the human body. These are the building blocks or the active units which actually learn information from the data that have been fed it. These neurons then are wired together to make neural networks, and these neural networks are the most popular class of deep learning algorithms. What does a machine learning model built using these deep learning techniques, that is, neural networks, look like? Let's first consider it to be a black box. You feed in a corpus of images for training this neural network, and as a result, you get an ML based classifier. We'll once again stick with the classification example that we've spoken of so far. The architecture of a neural network basically comprises of a number of layers of neurons, which are the active learning units. These layers are such that every layer has its own objective and has its own specialization. At a very high level, A neural network that you've set up for an image processing problem might have its first layer focus on the pixels of the images that are fed in. It'll have layers which come after that, and the next layer might focus on the edges. Notice that the output of the first layer feeds in as the input to the second layer. Each layer focuses on extracting more and more complex information from the input image. Pixel information is very simple and straightforward. Pixels come together to make edges, edges come together to make corners, and all of these put together comprise of object parts. This is how your image recognition system can identify eyes, ears, nose, etc. All of these layers of a neural network put together form the feature selection as well as the classification algorithm or the image recognition algorithm. This is, of course, an analogy at a very, very high level. We'll understand how these learning units work in just a little bit, but this should give you a big picture understanding of how neural networks work. Some terminology that you'll need to know. The first and the last layers of the neural network, that is the layers to which you directly feed in data and the layers from which you receive the output, are called the visible layers. This is because you can actually access the input to the first layer and the output of the last layer. As for the other layers in the neural network, and there can be many between the input and the output, you can't directly access the values of these layers. These are called the hidden layers. Depending on how complex the problem you want to solve is, you can have any number of layers within a neural network, and there are also specific architectures that we look at later on in this course. A neural network with many layers is called a deep neural network. A neural network with fewer layers is called a shallow neural network. Let's take a double click and look at what's inside each of these layers of a neural network. Every layer is made up of many active learning units called neurons. Neurons are ultimately just mathematical functions. We'll see that in much more detail in just a little bit. But each layer can have many, many neurons, and all of these neurons in different layers are connected to each other in a very well defined way. The output of the neurons of one layer feed in as inputs to the neuron to the layer which comes after it. Neurons which are connected to each other are said to be wired together. In a neural network that is fully connected, you'll have every neuron from one layer connected to every other neuron in the layer which comes after it. This is for a fully connected neural network. You'll, of course, see other architectures of neural networks where every neuron will not be connected to every other neuron, but we'll discuss it when those come up. If you look closely at this basic structure of a neural network, you'll see it's nothing but a graph with nodes, which are the neurons themselves, and a graph with edges, which are the interconnections between neurons. And this happens to be a directed acyclic graph. This directed acyclic graph is the computational graph of our machine learning model, and you've already seen how TensorFlow works so far. TensorFlow works on executing these directed acyclic graphs, which is why they're such a good fit for building and working with neural networks. To summarize, a neural network is nothing but a computation graph with nodes and edges. The nodes are divided into layers, where nodes in one layer are connected to the nodes in the layer which follow it. The edges or connections within this computational graph are the tensors. Traditional machine learning algorithms rely on experts to determine what features are important, what features the model should pay attention to. Representation machine learning algorithms, of which neural networks is a very common and most popular example, basically determine what features are important by themselves. There exist feature selection algorithms which are built in as a part of neural networks, which make sense of massive data sets and determine what features are important and what features contribute to specifying the output prediction.